Okay, guys, so I was going to continue on with electrochemical cells and see if we can wrap that up. And we're actually getting pretty close to the end of the course, which is kind of nice. So let's share that screen. So last day we talked about electrochemical cells being sort of like two beakers. And we can actually cause a redox reaction to take place without the chemicals that are reducing and oxidizing actually touch each other. So if we look at just quick scenario here. Okay, and we've got some fluid in here, some water in here, and let's sort of make it's kind of rough and ready picture here. Let's talk briefly about maybe a different type of chemical than last time. So let's make one electrodes tin. So make this tin, and then let's say this is 1 molar tin 2 plus. And I better just make sure I choose something that's going to work here for us. Yeah, that would work. Let's do let's make this nickel, and then 1 molar nickel ions, and in the book that's nickel 2 plus. Okay, so there's our setup, and the question is, maybe something like which one's the electrode, which one's the cathode, sorry, which one's the anode, which one's the cathode, which way do electrons flow, what's happening to the electrodes, is one getting bigger, one getting smaller, and what do you think? What do you think? What do you think? Well, let's do our table first, okay? And then we'll make the salt bridge sodium nitrate, and we'll deal with that question we posed in the last video about nitrates. So let's take a look at our table here. So we have reduction, and we have oxidation. And once again, we have all 4 chemicals here, so we need to be careful how we write this here. The tin metal is -1,4. And then tin ions are there. So we have tin ions, and because we've got tin ions, and we have tin metal. And then the nickel, conveniently, is right here. That's nickel 2 plus. And that's negative 2,6, I think, negative 2,6. 2,6. And what's also interesting, we also have nickel ions here at 0.15, positive 0.15. And that's all the chemicals we have on the table. I don't want to write this over here. That I don't want to write tin 4 plus because I don't have any tin 4 plus. So I want to make sure I only write the chemicals that I actually have on here. Okay. So in order for us to have a redox reaction, you have to have something get oxidized and something that can get reduced. So the reduction chemicals are on this side. So we're going to look at I used to call them oxidizing agents. Highest one up would be the tin ions, and then the lowest ones down here would be the nickel metal. So I kind of got the idea that my spontaneous reaction should be the tin getting reduced and the nickel metal getting oxidized. So what would happen is the nickel would actually get smaller, the electrode would get smaller over time, making more and more nickel ions. The tin ions would migrate towards the tin electrode and start turning into tin metal, because they're going to go that way. The nickel is going to go this way. And of course, both these involve 2 electrons. So let's take a look here. So what's the anode? What's the cathode? Well, an ox cared. So the anode is oxidation, which is the nickel. So that must be the anode. And the cathode is reduction, so that must be the tin. So this is the cathode. And which way do electrons flow? So there's a little memory device for you here. I always sort of remember that they flow alphabetically. Or if you think about like electricity, you might have heard of AC before. So they actually always flow from the anode to the cathode, because the anode is where they are given up, and the cathode is where they're taken in. So electrons always flow from A to C, from anode cathode. So in this case, they would flow from the nickel electrode to the tin electrode. Okay, so what would happen to the tin electrode? Well, it wouldn't lose any mass. It actually would gain mass. It would get bigger. So over time, you get a layer of a layer of tin metal forming around that. But the nickel electrode actually would get smaller over time. So yeah, you actually would get a smaller electrode. And you might have heard of words like corrosion. That's actually kind of what this would look like. It would look all jaggedy and kind of narrow and stuff. And it may not be pointy like that, but it would get smaller over time. So what other questions could you be asked? You might be asked, what is the voltage of this battery? What would the voltage be here? Well, for the reduction reaction, it's negative 0.41, sorry, negative 0.14 volts. And the oxidation reaction we have to flip. So this becomes positive 0.26 volts. So this would be a very, very weak battery. So 0.08 volts. Oh, no, sorry, my bad. It's wrong button here. Sorry, guys. Just one sec. I lost my pen here. Oh, there we go. Sorry. Let's choose that one there. Sorry, guys. So that's going to be 0.12 volts. Sorry. It's not a very powerful battery at all. Okay, so that's that. And then what would the ions in the salt bridge be doing? Well, the sodium ions should be migrating towards the cathode. So the sodium ions would start to migrate in here. And they would be trying to replace the positive charge that's being removed as the tin is being reduced. And then in the other beaker, you're producing all these nickel ions. So the nitrate ions would migrate into here. Now, I have had students ask about the nitrate, and they sort of say, well, what about that video you did? Well, one thing I need to know about the nitrate is it's actually higher than the tin. Dun, dun, dun. And that might look like it poses a problem because you're thinking, well, if I produce nitrates or I pull nitrates into there, won't they want to be reduced before the tin because they would be higher up? And what you have to do, if you look on the table, you look really closely here, you'll see there's two nitrate reactions. Both of them involve H pluses, which means that you would have to have hydrogen ions available. And if you look right at the top of the table, notice it says the ionic concentrations are 1 molar. So that means you would have to have, in order for the reaction to appear here, you'd have to have 1 molar H plus present, which means the pH would have to be 0. So you'd have to be dealing with very acidic conditions to even consider the nitrate reaction. So we can actually ignore it completely because nowhere in the question are we told that the beakers are nitrate, or sorry, nowhere are we told that either beaker is an acidic solution. It doesn't say it's an acid or anything like that. If it did say acidic, then you actually would have to worry about the nitrates. So generally speaking, if you use water, then nitrates can be ignored because they cannot undergo reduction without the presence of hydrogen ion there. Ooh, beep, beep. Okay. So let's just move on to one other question here. Let's take a look at a chart here. Let's say you're told you have a cathode, you have an anode, and you're told that the cell voltage are various amounts. So voltage. Okay. And let's say you're told that the cathode is a chemical called E, and the anode is a chemical called Q. And the voltage on this is 0.75 volts. Okay, so you have some battery. So like there's your voltage right there for this battery. So you have an anode called E and a cathode called E and an anode called Q, and the cell voltage is 0.75 volts. And then you have another cathode, different experiment called, let's say, M. Okay, and if you make the anode still Q, so you keep it the same anode, same material, then you get a voltage of 0.49 volts. And in our last experiment, let's make this still M here, but let's make an anode called, let's say R now. And you're told the voltage on this is 0.61 volts. Okay, so there's sort of some data here for us here. And you're going to be asked a question that is, let's assume that besides having these anodes and cathodes, you have the corresponding ions in solution with them at 1 molar. So what I mean by that is, you go back up to the picture here, we had a tin electrode and 1 molar tin ions. We had a nickel electrode and 1 molar nickel ions. So let's say that E is, you have 1 molar E plus, you have 1 molar Q plus, 1 molar M plus, that's gonna look weird, and 1 molar R plus. So you have their corresponding ions in solution, okay? So what we have to understand here is what would be the reduction chemical and what would be the oxidation chemical. So once again, an ox cared. So an ox cared. So that would be reduction at the cathode. So I know that this is where reduction is going to happen. And this is where oxidation is going to happen. So what I'm going to do now is I'm going to try to write these half cells in sort of a random order and see if I can make sense from the data table here. So I know that I would have E plus 1 electrode in equilibrium with E. So that would be like a half cell you would see in the data booklet. And then I would have maybe M plus 1 molar, with 1 E, equilibrium with M. And then let's use Q. So let's say Q plus ions, 1 electron, equilibrium with Q. And then finally R plus 1 electron, equilibrium with R. Okay. Now I've written these completely random. I don't know if that's actually the order they would appear. So now what I'm going to do is take the information from the data table, from this data table, and see if I can make sense of where the placement of these things would be. So if E is the cathode and Q is the anode, that means that reduction has to occur for E and oxidation has to occur for Q. So right now, that's actually going to work out because E is here and Q is here. So if you put these two half cells together, E should get reduced or should undergo reduction, and Q should undergo oxidation because it's a step down reaction. So what I'm going to do now is I'm going to rewrite this over here, and I'm going to say that I have the Q reaction below the E reaction. And that would be spontaneous. And also what I know is the voltage here, this voltage is 0.75 volts. So that's the voltage between them here. Okay, so now let's move on to M. So I'm told that M undergoes reduction and Q undergoes oxidation, which means that the M reaction, once again, has to be above the Q reaction. So now what I need to figure out is, well, is M here? So is the M reaction here like it is on this table? Or could it even be higher than the E reaction? So that is like, do you think it's above the E or in between the E and the Q? And this is where the voltage matters now. So notice the voltage for this reaction is 0.49 volts, which is less than 0.75, which means the M reaction would be in there, and that would be 0.49 volts. So once again, E is being reduced, M is being reduced, or at least the ions are, and then you got the oxidation of Q for the first two examples. And then the final bit of information is that the M once again undergoes reduction. So that undergoes reduction. And then the R undergoes oxidation. So just by chance, I did kind of get generally the right order here. So I know that this chemical here would get reduced and this chemical here would get oxidized. So R has to be below M, but is it below Q also? What do you guys think about that? Let's do a little bit of math here on this. So I knew that it was 0.75 from E to Q. It's 0.49 from M to Q. So if I subtract 0.75 minus 0.49, I get 0.26. This is 0.26 volts. That's 0.26 volts. And now what? Okay, so I'm told that the voltage here is actually 0.61 volts. So that's definitely more than 0.26. So the R reaction would actually have to be below the Q reaction. What are the odds that I just wrote that out the correct way? It was supposed to be random. Honestly, it was really supposed to be random. So that would be from M to R. That equals 0.61 volts. Okay. So that's sort of the ranking of this. So let's say the question was, which chemical is the strongest reducing agent then? Which chemical is the strongest of the reducing agents? So once again, reducing agents, they wind up getting oxidized. So yes, they get oxidized. So the reducing agents would be on this side. Okay. And the strongest reducing agent one would be the one most likely to get oxidized, which is always the one that's lowest down on the table. So in this question, R would be the strongest of the reducing agents. You might need to rewind that video and just rewatch that again, because I think that is a little bit confusing. The strongest oxidizing agent would be the one most likely to get reduced, and that would be the one that's highest up on this side. So really, E plus would be the strongest of the oxidizing agents. Okay, so that's a fairly tricky question. Kind of combines everything you've learned before, and let's see if we can just do one more thing here. Yeah, why not? Okay, so I'm going to just talk briefly about what's called selecting preferred reactions. So basically, what if there's more than two chemicals? That can get reduced. I should say more than one chemical, because you could just have two you have to choose from. More than one chemical that can get reduced or oxidized. Okay, so let's say that you had a beaker and you did a battery kind of thing here. Let's say you had your probe in here, and then a voltmeter right there. I squished that in pretty good, didn't I? And then you got your other electrode in here, and your water level would have to be pretty high up to cover the salt bridge. Okay, and let's say that you have, let me just think here for a second. How would I want to do that? Yeah, let's do that. Let's say you had aluminum here. It's aluminum, and let's say this was 1 molar aluminum ions. Okay, and let's say now what you did here, you made this beaker on the right hand side. Let's say you made this copper and 1 molar copper ions. And so right now this question is basically identical to the ones we've done before, but let's add a second electrode now. Let's add another electrode into this beaker here. Okay, and let's make this electrode out of, again, I'm going to choose a chemical that's going to work nicely for us. Here's that one. Let's see here. Going blind. Let's make it out of iron, Fe. And we also put in 1 molar Fe ions into solution. Fe3 plus. Ooh, Fe2 plus. Sorry. Let's go Fe2 plus. Okay, so in the beaker we've got copper ions, and we've got iron ions, and in the other beaker we have aluminum ions. Okay, and the question is, what do you think would happen here? Like, which thing do you think would get reduced? Which one would get oxidized? Do you think one of the electrodes would get bigger or smaller? and those kind of questions there. So let's once again let's set up our table here. So we've got reduction, and we've got oxidation, and once again I just write them as highest to lowest. So I have aluminum ions, so they actually are quite far down, I know that, and I have the aluminum metal. And then I've got iron, which is a little bit higher than the aluminum. And then I have copper. So I have Cu2+, and where is it here? Copper metal. Actually, I have Cu2+, and then I have Cu2+ and copper metal. There's actually two Cu2+. The Cu2+, below it actually goes to Cu1+. So I'm not gonna write that in because I don't have that chemical. Okay, so which things do what magical things that they do? Well, the things that are higher up on the left side, they should wind up getting reduced first. So I'm thinking the copper is going to get reduced. Okay, and then the aluminum is going to get oxidized here. It's going to get turned into aluminum ions here. So the aluminum is going to shrink in size. Yeah, okay. And then the copper ions are going to migrate towards the copper electrode, and they're going to plate onto that. And so you're going to get a layer of copper forming around that electrode there. And so what actually happens with the iron is absolutely nothing there. We just kind of hang out there. Now, I guess once you run out of copper, though, like if the copper ions went to zero, then the iron ions would start to undergo reduction then. And so I'm gonna do one more change here. I'm gonna mix up a few things here, keep the same chemicals that I have. I'm gonna keep the same chart here because I want to make sure we sort of understand this scenario. I'm going to erase what we've just done here. So you can always go back and rewind that if you want. And let's just switch things up a little bit here. Let's get rid of all this here. And let's say that we use the exact same chemicals, but we switch how we have them present. Okay, so let's make the beaker on the far side. Let's make this the copper, and then the copper 2+. And then let's make this the iron again, and the Fe2+ in solution. And then let's make this the aluminum, and aluminum 3+. Okay. And besides that, we're not going to find out what the voltage on this would be here. Okay. Well, since we have the same chemicals, the copper still has to get reduced here. So I would think the copper is going to go over here. It's going to plate on the surface. You're going to get a larger electrode here, and that's the site of reduction. So that makes that the cathode, whereas it was switched the other time. Now what's happening on the far side? Well, you've got iron and aluminum that can be oxidized, but the aluminum is lower down. So the aluminum, once again, should wind up getting oxidized here. So this electrode would get smaller and smaller over time. Now the aluminum reaction is negative 166, negative 1.66, and the copper reaction is positive 0.34. So if I take a look at 0.34, and then I add 1.66 volts, we're going to get, where are we here? 2. That's nice. 2 volts. Okay. And this battery would be a 2-volt battery. But if you notice what was happening here is the aluminum is getting smaller and smaller and smaller. And at some point, you're going to run out of aluminum metal. And so let's say that the aluminum is gone now. So it just gets, smaller and smaller and smaller. And eventually all that aluminum metal is gone now, or at least what's in solution. So you might have like a chunk of aluminum metal just kind of hanging there, not touching. Well, now what happens is you have no more aluminum. Aluminum's gone. So would the reaction stop? Would the battery just go to zero? Well, no, because you'd have this other metal that could wind up getting oxidized here. So the iron ions, they're at negative 4.5. And so what would wind up happening now is now the iron metal would start undergoing the oxidation process. And this actually is a really important thing to keep in mind because we're going to look at some practical aspects of some practical aspects of what's called giving other metals the chance to be oxidized over others, and it's sort of an important thing that we will see in the next next video we put out here. So this video really is just to quickly talk about batteries again, just talk about electrochemical cells, how to find the anode, how to find the cathode, what's the flow of electrons here. So once again, these would have been the anodes on this side because they're undergoing oxidation. So electrons would have flowed from anode to cathode. So they're basically, electrons are being taken from the aluminum and maybe the iron and being transferred to the copper electrode, where the copper ions wind up getting reduced. Okay, so I'm going to stop the video there and have a good night.